Okay, so in this class, we're gonna look at the dynamics of wireless channels, right? So before we take a look at that, we're gonna have some assumptions, right? So we're gonna assume narrowband transmissions, right? So narrowband means the bandwidth for the channel is very small. When I say small bandwidth, that means it's in terms of kilohertz. If if I say wideband transmissions, then I refer to the transmission with bandwidth in terms of megahertz, but this one is in terms of kilohertz, right? So remember from last time, right? We can think of the channels as system, right? Linear system actually. So we can take a look at impulse response, right, of this system of these channels. So how do you find impulse response? You just send a test signal, right? So the test signal is the impulse, right? This delta t that is, has amplitude infinity, and the width is almost zero at time zero. Okay, so you send this signal right to the channels, and at the end, the receiver right will receive this response, right? This is what we call impulse response. So in this case, you see that there are one, two, three, four, five impulses. So from one, it becomes five. How does that work? Because the channel has multi paths, right? That's why we have this different paths. Okay, and for example, this path, right? The delay is nothing, right? So we send at zero, we receive at time zero. The second impulse, there's a little bit of delay. The third, there's more delay, right? So different paths has different delays, okay? And you see that the impulse has different amplitude, right? Because of the different path loss, okay? Now, if the system is narrow band with small bandwidth, you can think of it as camera with very small number of pixels or very low resolutions. So that means if these five pulses are close together, the system will not be able to distinguish them. So seen through the system, right? The system will look at all of this as one pulse because they cannot distinguish all of them, right? So this one pulse is the sum of all the paths, right? So here sigma means the sum, right? You just sort of add all this together, okay? So there's only one channel gain or one path, right? Or one filter tap, right? So if you think of the channel as a filter, there's only one coefficient, okay? So I let G be this channel gain, right? So you can think of this channel gain has two different parts, right? So the first part is path loss, LP, right? You remember LP, right? Path loss. That's from before the midterm, right? So if the system, if the distance is increasing, path loss will be increasing too in terms of dB, right? So this LP, right, change with last distance, right, or time. This is what we refer to as large scale fading. Okay. The other component is this the sum, right, of all paths here, right here. So actually, it's a complex number, right? So when you add all of this, there might be different phases. When you add them, right, there might not be going in the same direction or same angles. Some of them might cancel one another out, right? But you add all of them, right, and then you take absolute value, raise it to power 2, right? So this is a positive number, right? Only positive number. So all of these are only positive number. Okay. Now we refer to this, right, the second part, which change with small distance or time, right? So if you move just a little bit, or the time change just a little bit, then this variable, right, or this gain can change by a lot. Okay, so that's the dynamic of this wireless channels, right? So we refer to this as small scale fading. Small scale means you change the distance just a little bit or just a little bit of time. This number can change by a lot. Large scale fading means this LP you have to move in terms of 10 meters, 100 meters, right, or several hundred meters so that the loss will be obvious. Okay. Anyone has any questions here? Okay. Now we're gonna focus on just the small scale fading, right? So just this part. We want to know the behavior of this, right? How does it change with the time, right? So we can assume some simulation model, right? We can assume that this paths there are going to be a lot of them. So when you sum them up, this is going to be complex Gaussians. Okay. Okay. So we're going to focus on the time dynamics, right, of this variable, which is we just look at the magnitude, right? So we're going to use this r, right, to denote the magnitude of this coefficients, right? And we want to find RMS. What is RMS? Anyone know? Right. So root mean square. What does root mean square means? It's a way to do averaging, right? So how do you do this averaging? So imagine, right, we're tracking this variable r, right, or this variable, right? It's going to be changing in time, right? So we want to find the average. Maybe this is the average, right? Root mean square. How do you find this? First, you take this value, right? You sum it, right? Sum it using integral, right? And then divided by the time, right? So you integrate from 0 to t, you divide by 1 over t. And then you take a square root, right? So this is where root mean square come from. Root means square root. And you want to find the mean square, right? Mean square, okay? And then what do you do? What is this? Lim t to infinity, what does this means? Anyone? You take the limit, you take t to be very big, right, to infinity. So you're looking at not, finite time, you look at the whole time, right? You find the average of the whole time, okay? So you end up with some number, that's gonna be the average, okay? Now the question here is, you want to know how many times, right, on average, that this channel gain, right, or the magnitude of the channels fall below some number, right, on average. So this number, right, RTH, maybe it's right here. You want to know when is the channel dip below this. For example, right here, right? So this is one time, yeah? And how long it stay below, right? Because that's going to indicate how good or how bad channel is, right? So if it dip many times, that means it's going down very often, so that's not good, right? Or maybe that's good, right? Or how long does it stay below this threshold, right? So how long does this stay below this threshold on average, right? So how do we answer this, right? So there's some assumption that we have to make. First, the channel will look something like this. So what's this? You see that there's a transmitter, there's a receiver. There's a lot of object in between, right? So you see that there are a lot of paths going from the transmitter to the receiver, right? So H is the sum of many paths, right? All of this is what we call non-line of sight paths. What is non-line of sight? What is NLOS? So line of sight means this, right? I'm looking at you, right? It's direct path. Non-line of sight means it's not direct, right? It's going, tangent, right? Going somewhere else first, right? Yeah. So all of this will have similar power, right? It's all small power and you add them together. They're all random, right? So this H is going to be complex Gaussian. And this is what we call Rayleigh fading. So when I say Rayleigh fading, you think of it in these situations where there are a lot of paths and there's no line of sight path. Okay? Now, the way you're going to look at this changing of this, channel gain in time, one variable or one parameter that we can look at is what we call level crossing rate. Okay? Level crossing rate. So what is this level crossing rate? We use LCR, right, to denote this, right? So it's the average number of times per second that the magnitude of the channels crosses the threshold. Okay? When this is bigger than 0. So what is this? What is dr over dt? Anyone know? It's the derivative, right? You differentiate r with respect to t. When you differentiate, what do you get? Slope, yeah, slope. So we're gonna take a look at when slope is bigger than zero. Let's imagine this. So you see here, if we look at the slope, what kind of slope is this? When it's going down, is it positive or negative? So this is negative. When it goes up, what is the slope? Positive. So when r is coming down below the threshold and then going up, we count this only one time. We count when the slope is bigger than zero, right? So we count this. We don't count this. Everyone got this? Okay. That's why it has to be there. Okay. So what is level crossing rate? We use n subscript r to denote level crossing rate. We can analyze this for Rayleigh fading, right? It's equal to square root of 2 pi multiplied by fm. Okay, what is fm? Anyone remember? From last time, what is fm? It's maximum dropper shift. Okay, so what is maximum dropper shift? You can compute it using this formula. Fc multiplied with V divided by C. What is Fc? What is Fc? Carrier frequency. What is V? Relative speed between the transmitter and the receiver. What's the C? Speed of light, right? So here this is in terms of hertz, right? Or per seconds. Okay? What is this? RTH is the threshold, right? Depending on what you want to set, right? Below the root mean square, right? RIMS, this is gonna be the average, right? Average root mean square. So RTH divided by RIMS, this is always gonna be less than 1, right? Because this is bigger, this is smaller, this is less than 1. Okay? And then e to the power of minus RTH over RIMS raised to power 2. The unit here is number of times per second or hertz, right? Hertz. Okay? So this is what we call level crossing rate. So that means the channel will cross the threshold very quickly if the maximum dropper shift is large, right? So if this FM is big, channel change very quickly, right? Very fast. Okay. Okay, let's do some example. For example, if we set this threshold equal to the root mean square, right? We set them to be equal. That means the ratio is equal to 1. Let's say the maximum dropper shift is equal to 80 hertz, right? So we can use this formula, right? So square root of 2 pi, yeah? Fm is 80, yeah? This is equal to 1, right? Okay. And then e to the power of minus 1. Okay. So you can compute this, and the answer is 73.77. So what is this? This is the number of times that the channel gonna dip below the threshold, right? 73.77 times per second, right? So that's a lot, right? So that means the channel change very quickly. Why? Because if you look at maximum dropper shift, this is a big number, right? 80 hertz. Any questions here? Okay. Now, let's set the threshold to be smaller, right? So you say RTH is divided by the mean, right? It's equal to 0.1, right? So that means the threshold is even lower, right? So if it cross this threshold, that means the channel is really bad. Okay? And again, FM is equal to 80 hertz, right? So we want to find NR, right? So we use the same formula, right? Square root of 2 pi 80, this is FM. Now the ratio is 0.1, and then e to the power minus 0.1 square. Okay? So you use your calculator to compute this, you got 19.85 times per second. You compare with these two numbers, which one is bigger? Which one is bigger? This one or this one? This one is bigger, right? Well, it's not surprise because you lower the threshold. So the number of times that the channel will dip below that threshold will be less likely, right? Okay. The other variable that the other parameter that we want to look at is what we call average fade durations. That is the duration or the time period for which the channel, right, is below the threshold. This is not the number of times, but it's the time itself, right? How long does it stay below the threshold, right? So you use this tau with the bar, right? So tau bar is equal to e to the this ratio, right? R threshold divided by RMS to the power 2 minus 1 divided by this, and then Fm, and then square root of 2 pi. Okay. So on the top, there's no unit. This is no unit. Square root of 2 pi is no unit. What is the unit of Fm? Hertz. So 1 over Hertz. What is 1 over Hertz? Right. So the unit of this fade duration in terms of seconds. Okay. So let's look at the same example, right? So Fm is 80, RTH over RMS is equal to 1. So if you use the formula, right, tau bar is equal to this, right? So you use the formula that we just talked about, right? E to the power 1 minus 1 over 1. So this is 1, right? Fm is 80, square root of 2 pi. The answer is 8.57 milliseconds, right? So that means the channel cross below the average, right? And stay there on average 8.5 milliseconds before it goes up again. Okay? If you set this ratio to be 0.1, the fade duration is reduced. Now it's only 0.5 milliseconds, right, on average. Okay? So the channel is changing. It's mainly affected by what we call maximum dropper shift.